Let's think about the fight against cancer for a second, but let's frame it like a military campaign. For decades, the main strategy was just brute force. But in the battle against one really specific enemy, acute lymphoblastic leukemia, the rules of engagement have totally changed. We've gone from carpet bombing to surgical strikes. So let's dive into this incredible story of medical warfare.
First things first, we have to understand the stakes here. Acute lymphoblastic leukemia, or ALL, isn't just some rare disease. It is the single most common form of childhood cancer. It makes up almost 80% of all acute leukemias in kids. So yeah, this is a battle we absolutely have to win.
So who is this enemy we're talking about? Well, ALL is a cancer where the body's factory for making blood cells just goes completely haywire. Instead of producing healthy white blood cells that fight off infections, it starts pumping out millions of useless, immature cells called lymphoblasts. They grow super fast and they crowd out everything else. And that's what makes this disease so dangerous.
Okay, so to win a modern war, you don't just need bigger weapons, right? You need better intelligence. The real breakthrough in fighting all came when we stopped seeing it as this one single enemy and started, decoding its genetic playbook.
You can even see this evolution in the diagnostic process itself. Now, biopsies and cell analysis, those have been standard for years. But it's that third step you see here, the genetic analysis, that changed everything. It's the difference between just identifying an enemy soldier by their uniform and being able to read their secret communications.
And that unique genetic fingerprint, that is the absolute key to the new strategy. See, by identifying the specific mutations that are driving the cancer, doctors can pinpoint its Achilles heel. It showed us that ALL isn't just one enemy, it's a bunch of different factions, and each one requires its own unique battle plan.
In this table here, it shows just a few of those enemy factions. The most famous one is probably Philadelphia positive, or Phi-positive ALL. It's defined by this one specific genetic mistake where two chromosomes literally break and swap pieces of their DNA. This single error creates the engine that drives the cancer. Finding it was the key to a whole new way of fighting.
Which, of course, brings us to our weapons. For decades, the only real weapon we had was chemotherapy. A powerful tool, for sure, but a very blunt instrument. But now, thanks to all that genetic intelligence, we've developed guided missiles.
This slide really gets to the core of the whole story. On the left, you've got the old way, chemotherapy. It's like carpet bombing an entire city just to destroy one building. I mean, it can work, but the collateral damage to all the healthy cells is just immense. Then on the right, you've got the new way, targeted therapy. This is our guided missile. It homes in on the cancer's unique genetic signature, leaving healthy cells pretty much untouched.
So what exactly are these guided missiles? Well, for Fib-positive ALL, they're a class of drugs called tyrosine kinase inhibitors, or TKIs. And how they work is just brilliantly simple. They find that specific protein made by the Philadelphia chromosome, the very engine of the cancer, and they just jam it. They shut it down completely.
To really get the impact of this, you have to look at the battlefield before TKIs came along. For patients with Ph-positive ALL, the 3-year event-free survival rate, and that means they were alive and without a relapse, was a pretty grim 35%.
And after? By adding these targeted TKI missiles into the chemotherapy arsenal, that same survival rate skyrocketed to over 80%. I mean, what an incredible leap forward. And it was all thanks to that initial genetic intelligence.
And hey, this isn't just hype. The official clinical guidelines from the National Comprehensive Cancer Network state it plainly. They say the emergence of targeted therapies represents an important advancement in ALL therapy. This shift is truly one of the most important breakthroughs in modern cancer treatment, period.
But even with guided missiles, how do you know the war is really over? That's where something called minimal residual disease, or MRD, comes in. You see, after treatment, a few cancer cells can hide out, almost like spies. Standard microscopes can't even see them. MRD testing is like a super high-tech surveillance scan that can detect one cancer cell in 100,000, telling doctors if there are any enemy combatants left.
All right, so we've decoded the enemy and we've built precision weapons. What's the next frontier? Well, it's even more radical. It's turning the patient's own body into a highly trained, cancer-seeking army.
And this is really where science fiction becomes reality. I mean, what if instead of giving a drug to the patient, you could turn the patient's own immune system into the drug?
This is the process for what's called CAR T-cell therapy, and it is absolutely mind-blowing. Doctors collect a patient's own T-cells, the soldiers of their immune system. Then, in a lab, they reprogram them. They give them a brand new targeting system, the CAR, that can recognize the leukemia cells. Then they grow millions of these new super soldiers and infuse them back into the patient, where they literally hunt down and kill the cancer.
This is a true living drug. The cells can multiply and keep on fighting for months. It's a total game changer for patients whose cancer has come back. But a weapon this powerful also comes with serious risks, like something called cytokine release syndrome. It's basically a dangerous friendly fire incident where the supercharged immune response goes into overdrive. It requires incredibly specialized care to manage.
So, where does all of this leave us? Well, we've gone on this incredible journey from a blunt, one-size-fits-all war to a deeply personalized, intelligence-driven campaign against leukemia.
And this slide really illustrates the new definition of victory. The goal isn't just to eradicate the cancer anymore. It's to do it with less collateral damage, to manage side effects so that survivors don't just live, they live well.
But the war is not over. This chart shows a major challenge we still face. While about 60% of pediatric patients enroll in the clinical trials that drive all these amazing innovations, only a tiny fraction of adolescent and young adult patients, AYAs, do. Bridging that gap is absolutely critical if we want to bring these advanced weapons to everyone on the front lines.
Ultimately, this whole revolution in fighting leukemia proves that, by understanding a disease's fundamental genetics, we can design smarter, more effective weapons. And it leaves us with a final, really powerful question. If we can do all this for leukemia, what other unconquerable diseases are out there just waiting for us to find their genetic weakness?